Today, we want to keep thinking about vector fields, and we want to talk about all the different things that we'll be thinking about once we can imagine a vector field in place. So, to each point in R2 or R3, we are assigning a vector, and we can imagine the flow of water on the surface or the flow of air in a room. And at each point in the room, the vector field is saying the air is going this direction. And so it's assigning a vector. And the magnitude of the vector would mean that it's really windy at that spot. The magnitude of that vector would indicate how windy it is at that spot. So right next to the vent, we'll see these long vectors coming out of the vent. Maybe down here by the floor, we won't see as much draft. So the vectors will be shorter and indicating different directions. So that's what we want to think about in terms of a vector field. Every point has some vector attached to it. Here are the things that we want to think about in terms of the vector field. One of those things is the flow of the vector field. We want to think about the flow of the vector field. If we just drop a leaf on the water, or if we imagine a mote of dust floating about the room, what path would that leaf or that mote of dust take as it just follows the vectors around the room? So what path will a mote of dust take as it just follows the vectors along the surface of the water or around the room? Mote of dust. So we want to think about the flow of the vector field. For example, if there's a piece of dust just floating around the room, and it's only subject to the air current, at every point, it just starts going in the direction of the air at that point. Now, the vector field is changing continuously, so as soon as it moves a little bit, it finds another vector and just starts following that direction. And so we'll be tracing this path around the room. And the path that it follows will depend on what the vector field looks like, and it'll depend on where we start. So there'll be all these different paths if we start at different locations in the room. So maybe there's a point in the room where the vector field is equal to 0. And a piece of dust that lands there would just stay there because the vector field says no direction here. But a mote of dust by the vent is going to go directly down because the air is pushing it directly down. And then it'll slow down as it gets farther away from the vent. And we can imagine just a little dotted line, a little path as the dust flies around the room. So this is just the flow of the vector field. This we think of as the flow of the vector field. What kind of paths do we get just based on the vector field? So for a more visual example, let's suppose that at this point, the vector field is kind of going horizontal. And so we imagine a little piece of dust. It starts off moving horizontal, but then a little bit later, the vector field has curved. And then, so the dust kind of curves up a little bit. And then here, when we get to that point, you see the vector field is pointing directly up. And then over here, the vector field is pointing backwards a little bit because we've got this little eddy current. And so we can imagine if this is the vector field, the vectors that we run into, then this speck of dust would follow this kind of semicircular path. Yes. Yeah, we can imagine, so if there's a guy skiing down the slope, right? Then the vector field of the hill pushing back on the dude is gonna change as it gets steeper or flatter. So we can imagine different vectors on that surface. Yes, that's exactly a good way to think about it. That's an excellent way to think about it. We're thinking of this path, and it's kind of like we're building it in the other direction. Instead of drawing a path and drawing tangents at all the points, we're taking all these tangents and building the path, figuring out what the path should be. That's going to be the flow. So the path, the vector field will be tangent to the path. That's very good. Imagining the vector field tangent to the path. Now, one thing to note about the path that we've drawn here is that the path has a direction to it. So this is not just a semicircle. This is a semicircle, but we are going in this direction. So notice that the path has direction. Spelled path wrong. So we'll say that the path has an orientation to it, has what a direction that it's traveling. Now, the path that we get will depend on where we start and where that lands us in the vector field. So maybe if we start a little bit later, we see the same horizontal, but it goes up at a little bit less of an angle. And so we might be carving out a different path if we start a little bit to the left of where we're going and a little bit up. So maybe the path here would be slightly different. But we still have a direction on the path. So when we see all the vectors laid out, we want to be able to imagine all the different paths that could be there, depending on where we start. That's one thing that we want to think of. What is the flow of the vector field? Number two, suppose that we wanted to carve our own path through the vector field. Suppose we wanted to take our own path through the vector field. There's all this flow in the vector field. So another thing that we might want to do is carve our own path through the vector field. Then we can imagine at each point, how much is the vector field helping us on that path or pushing against us? We're walking through the room. Is there a tailwind or is there a headwind? Or is the wind coming at it, is a headwind, but not directly into my path, kind of at an angle? Or there's a tailwind, but it's not directly behind me. It's coming in at an angle. So here, we're making our own path, and we're thinking, how much is the vector field pushing us, pushing with us, or pushing against us? How much is the vector field helping or hindering our progress? So this is a path that we're making on our own. Like we saw on Tuesday, there's the high winds outside, and if we were going in one direction, then the wind was pushing against us. If we were going the other direction, then the wind was pushing with us and helping us out. So imagine in this scenario, I want to follow this path. So imagine in this scenario that I want to follow this path. Now down here on this line, I didn't draw all the vectors down here, but I was imagining just a bunch of horizontal vectors. So here at the start, the vector field is pushing against us because that green line is running tangent and in the opposite direction of the vector field. The vector field flattens out a little bit up here. So at this point, let's say the vector field is kind of flattening out. So in the beginning of this journey, the vector field is pushing against us. But we continue our path. And at some point, these vectors are turning around. So at this point, the vectors are vertical when we get to this point in the path. Maybe at one point, we're even perpendicular. But when we get to this point in the vector field, on the path that we want to take, we're more in line, we're more going with the flow of the vector field. And we want to calculate how much of this is happening. How much is the vector field helping us or hindering us as we make this path? Any questions? How much of the vector field is going in the direction of our path? That's one of the questions that we might be asking. How much of the vector field is going in the direction of our path? We're imagining how much of the vector field is in the direction of our path. The direction of our path is a vector. The vector field is a vector. How do we figure out how much of one is going in the direction of the other? What operation are we using here? The dot product. So this calls to mind the dot product. Now we want the whole thing. We want how much of this over the entire path? How much total help or hindrance over the entire path? Now when we're asking how much did the vector field help or hinder us over the entire path, what are we going to be doing? Well, we'll just take all these dot products and add them together. The complication being that the vector field and our path are both things that are changing continuously. So when we want to add up all the results of these dot products, rather than just use addition with pluses in between a bunch of terms, we have to switch to integration. So we want to find the sum of all these dot products along the entire path. We're going to have to figure out a way to turn this into an integration problem, because our vector field and our path are going to be changing continuously. Integration is addition when we don't have anywhere to put the pluses, because we're trying to add over a continuum. Integration is multiplication when one of the factors is continuously variable. This dot product, how much the vector field is helping or hurting our path, or helping or hindering our path, is a multiplication. It's a dot product. Any questions? Remember, the dot product is based on the cosine. U dot V oops, these are vectors. The dot product is based on the cosine. So U dot V is the magnitude of U times the magnitude of V times the cosine of the angle between the vectors. If theta equals 0, this is 100% helping. Cosine of 0 is equal to 1. So we're getting all of the magnitude of u and all of the magnitude of v, all helping. If we're at a point where our vector field, I'm going to use horizontal because one of them should be easy to draw. If our path is taking us 45 degrees, we are getting help. 70% of that vector field is pushing us along. We're getting 70% of that wind. If we're traveling perpendicular, it's not helping, but not hurting. When we pass 90, cosine drops negative. So that negative value is going to indicate that the vector field is now working against us. I just realized I drew these vectors in Nets colors. Yeah. Nets. You know why the Mets colors are blue and orange? No, because the Dodgers and the Giants left town. Once the Dodgers and the Giants left town, all New York had was the Yankees. And the only rivalry in baseball, the only real rivalry in baseball, left town. So they made up the Mets. And they're like, well, it's a National League New York team, so we'll use blue and orange. Yeah. Although Giants Dodgers, it just from my perspective, it seems like based on the games that I've been to, it's kind of a sad rivalry when half the rivalry isn't really into it. Like the Dodgers don't really care all that much. Dodgers fans really don't care all that much. But Giants fans super hate the Dodgers, and that's kind of sad. As a Giants fan, I'm kind of embarrassed for how much all that disdain that I carry for the Dodgers. Oh well. Any questions? Tom? Although I did go on a road trip, and I needed My friend and I did go to some games at Dodger Stadium. And I don't know if it's still true, but Dodgers fans show up in the third inning and leave by the seventh. So it's really easy to park and it's really easy to get out of the parking lot if you're going to stay for the whole game. There's a On the other hand, they keep talking about Dodger dogs. Not impressed. It's just a hot dog. It's like every other hot dog. Nasty. Costco hot dog is best hot dog. That one actually, there are two levels of hot dog. Costco hot dog, every other hot dog. Costco dog, every other dog. That used to be the play. Back when the Giants still played at Candlestick, whatever they called it after Candlestick, I can't even remember. But back when they played at Candlestick, this was like in the early 90s. Imagine like the 90s after the strike in 94, when they're trying to get people to come back. You used to be able to buy 2-for-1 upper reserve tickets. So it was like $7.50 for an upper reserve ticket, and you were getting 2-for-1. So it's $3.75 per ticket, upper reserve. So my dad, myself, and my friend, that's 3, but we had 4 tickets. So we just pre-made a bunch of hot dogs, put them in a cooler, and put the cooler on the seat in between us. That way we could have Costco hot dogs and be the envy of everybody else in the second. But because it was Candlestick in the early 90s, there weren't a lot of people there anymore. Is it AT&T? Well, the whole place is gone now. So, is it Oracle or AT&T? Mac Bell? Yeah. They play baseball at them. Kids are young. They used to play baseball at Candlestick. Have you ever been to Candlestick? So when you were at Candlestick, it was all closed. It was a complete bowl. It went all the way around, right? And it was still stupidly windy, right? There was one time when they were playing baseball, they really did play baseball at Candlestick. There was a pop-up, and I remember the pop-up went and Pete Rose caught it just behind first base. Pete Rose is playing third base on this game. But the ball went up. Pete Rose calls for it, starts tracking it. He's like, oh, no, I still got it. No, I got it. He catches it. He looks around. He's like, oh, what the hell am I doing over at first base? And everybody's like, oh, it's windy. So imagine how windy Candlestick is. That used to be open on one side. It was not always enclosed. It used to be just like one of those U-shaped ones where you could look out onto the bay and see like hurricane force winds coming into your face or blowing out, depending on what it felt like at the time. Anyway. My favorite would be going to a night game at Candlestick in the summer, because it'd be like July in Hunters Point in San Francisco. So I don't know if you've ever been there at night in July. It is cold as shit. I mean, it's there in weather, so layers, always layers. So we'd be a Candlestick and we'd be like wrapped up in like 8 layers, sitting out in the bleachers, and then interleague play happened. And there's this dude sitting next to us, and he's got like shorts on, loafers with no socks, and a cardigan. So, oh, visiting from Boston, I see. So yeah, at least this doesn't actually count as cold for you. He looks cold. Anyway, what are we talking about? Oh yes, blue and orange, Mets color. So We're looking at how a path might one of the things we want to look at is how a path might interact with the vector field. Press. Another thing that we want to think about vector fields. This one is going to be a vector field in R3. And we can imagine the vector field flowing through a surface. So maybe our vector field is just water flowing through a pipe like this. It's all nice and even. And we put a filter in. Something that the water is going to flow through, and we're going to measure that stuff. Let's just look at it from the side. So we're going to be interested in all these points on the surface, or on the vector field, on the surface, how the vector field is interacting with those points. So how does the vector field interact with the surface? What's happening as the vector field goes running into the surface? At each point on the surface. So at each point on the surface, we need a vector to represent the surface. This is our third question because we want to start thinking about the question itself and the source of each question. So I want to bring this point up. If this was a trial, I would not be able to get away with this. There'd be an objection leading the witness. Somebody go, we need a vector at each point on the surface. That's when they would object. Leading the witness. There's a Supreme Court ruling on this. Teachers can treat students as hostile witnesses, so I'm allowed to do that. So we want a vector at each point on the surface to represent the surface. And we want one vector. What vector are we going to pick? Any ideas? we're gonna pick the normal vector. Because I've got this surface, I need one vector at every point. I'm in 3 dimensions, it's a 2-dimensional surface. I've got too many tangents, so I'm just gonna go with the normal vector. So here at this point on the surface, the normal vector so at each point on the surface, we pick the normal vector to represent the surface. And then we look at what the vector field is doing at each of those points. So here at the, like the vertex of the little surface that I drew, the vector field is going right along with the normal vector. Angle between them is 0, we're getting all of it going through. But here, a little bit up higher, the vector field is coming through the surface at a little bit of an angle. So the interaction is a little bit different. But what we're looking for, because we're in calculus class and we're trying to do integration, and we know that integration is multiplication, but one of the factors is continuously variable. When vectors show up, the multiplication that we've been using is dot product. So here we go. We got a surface, we got a vector field flowing through the surface. We pick the normal vector at each point on the surface. The surface itself would be continuous, continuously variable, and the vector field would also be continuously variable. Then we just want to back away from the surface and think about the vector field going through the interior. So those are the 4 places where we're going to be thinking about vector fields and how they interact with various objects. We're going to have to do a lot of stuff here. We're going to have to figure out a way to describe a 1-dimensional path in 3-dimensional space. We're going to have to figure out a way to describe 2-dimensional surfaces in 3-dimensional space. But other than that, we're just going to be finding a bunch of dot products and adding them up with integration. That's going to do it for today. That's going to do it for this week. I will see y'all on Monday. I will be in my office tomorrow from 9 to 11-ish if you have questions. See you Monday.